Let's talk about energy. When you think about energy, most people think about this. You flip a switch, you get a light. You plug in a phone, it gets charged. You plug in your car, you can drive. That's how people think about energy today. But when I think about energy, I think about this. This star is 93 million miles away. It's 98.6% of all the mass in our solar system, and it just so happens to be a fusion reactor. It's responsible for all life on our planet. Those photons traveling through space and hitting this planet are converted by plants through photosynthesis into food, consumed by insects and mammals and fish and all other kinds of animals. And over time, they die and they decay and they become something very different. They became fossil fuels. Now, those dinosaurs had a pretty good run, a run of 162 million years. So if you want to talk about sustainability, that's a pretty good record. We've only been around for 100,000 years, and we're already moving into kind of dangerous territory. What that rule tells us is the law of mass conservation. So before Einstein, we had Antoine Lavoisier, who's the father of modern chemistry, who said that matter can neither be destroyed nor created. That if you put 10 grams of vinegar into a bottle and 10 grams of baking soda, you're going to get carbon dioxide, but you're going to get 20 grams of it. But when you get into the atomic level, something changes. And that's what Einstein figured out. Energy is defined as the ability to perform work. If you lift a kilogram up a meter a second, that's considered a watt. Throughout time, we've always looked for substitutes for our own labor. We've put domestic animals to work to plow our fields, to pull our carts. We've discovered that if we burn wood, we can heat our homes. Later, if we burn coal, we can actually feed machines. We invented the steam engine to pump water out of coal mines so we can continue to extract a higher form of energy density, dense fuel. Over time, we went to fossil fuels, ran diesel machines, and on to today, where we get into the atomic era, where we've been able to split the atom and create a tremendous amount of power. Now, to kind of put this in perspective so you understand these different levels of kind of energy evolution, think about a very basic measure, which is the BTU. How much energy does it take to elevate a pound of water by 1 degree Fahrenheit? That is a BTU. And if you look at these different fuels, you can see the level of energy they have stored inside. And it gets increasingly higher when you move to more energy-dense fuels like coal and like oil. But the difference between mass conservation at the chemical level, where you're converting coal or wood into hydrocarbons and energy, and the atomic level is that the first is rearranging atoms and forming new compounds, but the second is digging in to the nuclei of the atom and relieving what's called the strong nuclear force. That's what happens when you get to fusion and fission. And fusion is 10 million times more energy dense than oil or a chemical process of burning hydrocarbons. So there is one great invention that took place after the Manhattan Project, and that was can't say the invention, but really the discovery and exploitation of fission. Now, fission, we all know, is a neutron splitting a nuclei. And when this happens, a tremendous amount of energy is released and a number of neutrons. There's two types of fission. There's controlled fission, like you have in a nuclear power plant, and there's uncontrolled fission, like you have in an atomic bomb. Now, the energy that's released is equal to the mass of these atoms multiplied by the speed of light squared. It's a tremendous number. It's a 0% carbon product, but fission today produces radioactive waste. Fission has, the byproducts from fission last hundreds of millions of years, and they're radioactive and they're dangerous. So that's the bad part about fission. But there's an alternative to this, and that alternative is fusion. Fusion is extraordinarily different because fusion is replicating the sun. And what does the sun have? Well, it's got a vacuum of space. It's got a lot of fuel. It's, a million times bigger than the planet Earth. It's 98.6% of all the matter in our solar system. It's filled with hydrogen and helium, and it's got a tremendous amount of gravity. That gravity pushes these atoms together. They overcome the Coulomb barrier, and they merge. And when they merge, the energy they produce is equal to the sum of those two atoms minus the new atom that they produce multiplied by the speed of light squared. And as we know, that's a very, very big number. So our job is effectively to put a star in a jar and to contain that here on Earth. And what's involved in doing that? We were taught in school that there were three types of matter. We had liquids at room temperature with water, you had a solid when you freeze it, and you have a gas when you put it on the stove and you're going to make a cup of tea. But there's another form of matter which is called a plasma. And a plasma is what happens when you superheat gases and they get stripped of their ions. And that's what's going on in that sun. It's a plasma. It's not a gas. We call it superheated gas, but it's a plasma. And the core of the sun's at 15 million degrees C. Now that's enough to fuse atoms in the sun because of the immense amount of gravity that pushes them together. But if you don't have that immense amount of gravity, you have to make it up in another area. You have to make it up using magnets, and you have to make it up using heat. We can't match the gravity magnetically, but we can increase the heat. So there's a couple of different approaches to fusion on Earth, and each approach has its own positive and negative events, right? The two on the left and the one in the upper right-hand corner, all have something in common. They produce neutrons. And neutrons are radioactive. And when they hit a material, they impart that radioactivity to that material, and that material begins to decay. And this is what nuclear waste is, and this is why we don't like it. But the half-life of tritium in this event is 12.3 years. The half-life of uranium is 100 million years or more. So there's just no comparison here. You could take nuclear waste from a fusion reactor that's using tritium, and you can bury it in a paint can for 25 years and forget about it. It's not a problem. On the bottom right, you have what's called aneutronic fusion, which is boron and hydrogen. The great thing about these two elements is that when they merge, they produce helium. So in addition to producing an immense amount of energy and light and heat, you can also blow up balloons. Which I think is the main reason we need to do this, obviously. So this is what happens when deuterium and tritium fuse. Those two atoms come together, they fuse together, they produce 14 million electron volts of neutron energy and helium. When you have proton boron fusing, you get less energy, you get 8.7 million electron volts of energy, but you get 3 alpha helium particles, and you get no neutrons. And the other thing that's really interesting about boron and hydrogen is that helium is a charged particle. A neutron has no charge, it's neutral. But when you have a charged particle, you can mess with it magnetically. Now, if anyone here drives an electric car, you know that when you take your foot off the gas, that the car will slow down because it's taking the kinetic energy of the vehicle, channeling it back into the motor and converting that kinetic energy into electricity. We could do the same thing with the charged particles from helium inside of a reactor. In addition to capturing all of the heat that's happening in this 1 billion degree vessel. Now, as soon as I say 150 million degrees for DT or 1 billion degrees for boron, everyone's heads explode. And they're like, how is this even possible? The sun's at 15 million degrees C. You can't have 1 billion degrees. There's no material in the universe that can, sustain those types of temperatures. And that's a very true statement. You can't. But what you should understand is that there's so much energy locked into this stuff, but it's very, very small. A single grain of sand on the beach here has 60 quintillion atoms in it. When you have things operating at the atomic level, such as these arcs inside of a noble gas, this electrode here that's activating atoms inside of this, these arcs, these little bolts of lightning, are at thousands of degrees Fahrenheit, but you're touching it with a finger. It's not transmitting that temperature to your finger. Has anyone ever licked your fingers and snubbed out a candle? You basically put out 1,600 degrees C of heat with your fingers. Why did you not just burn the hell or melt your fingers to nothing? Because it's very low in density. And so I have to say that what we're doing in these nuclear fusion reactors is we're dealing with very, very low density materials because they're at the atomic level. And so that's something that we have to consider. And that's why we can contain this energy, but we do it not with a piece of steel like you see here. We do it with a magnetic cage. So surrounding a tokamak like ITER in the south of France, or surrounding this device, which is called the field reverse configuration reactor, it's a linear device. It looks like a hydro flask, right? It's surrounded with electromagnets that create a magnetic field. And then when you push your superheated gas or plasma in there, it goes inside that magnetic cage and it rotates. In fact, let's take a look at what that looks like. This animation's never been seen before, except for by the guys I worked with to create it. And it shows you what happens when you put a plasma inside of a field reverse configuration and you start to hit it with a particle beam. That plasma looks a bit like a football, and it starts to heat up, and it's rotating away from you. And if anyone remembers their electronic classes, you have the right-hand rule. So if the current's going this way, it's swimming around and making a magnetic field in that direction. And what happens in this is it goes to the end of the plasma, it rotates, and it turns direction and goes back down through the center of the plasma, and it changes polarity. So you have a plus on the outside and you have a minus on the inside, and all of the atoms inside of that cloud, which are hydrogen and boron atoms, are being contained and held by the magnetic field that's being produced by the plasma itself. The red lines outside are the external magnets that are kind of holding everything away from the walls of the vessel. So this can be at 1 billion degrees, and it can be at a temperature that allows those hydrogen and boron atoms to fuse and produce those 3 helium particles, which can be decelerated and turned into electrons, and a tremendous amount of heat that can be converted into steam and drive a turbine. So, where do we go from here? Well, here's a picture, or actually a movie. This is animation. This is real life. This is what a plasma looks like in an FRC. And it's slowed down millions of times because the entire duration of this in our machine was about 40 milliseconds. And this was at about 75 million degrees C. So we're now in the process of building the next machine that's going to go to 150 million degrees C, which will prove that we can get to the temperatures required to fuse deuterium and tritium. And then we're going to go to 1 billion degrees C, which is going to enable us to fuse hydrogen and boron. Now, why did I talk about EMC squared and laws of mass conservation? To know where we're going, we have to know where we've been. Where we've been is one of the billions and trillions of stars in the universe. All of us come from those stars. The solution we're looking for to have sustainability on this planet is one where energy does not deplete our resources. Because energy and mass are equal, it's a cycle. We have all the energy we want because we have plenty of matter we can turn into energy that can then turn into matter, then turn into energy. That's the cycle we need to be able to achieve long-term sustainability on this planet. When we get to a fusion reactor that is modular and can be shipped to Bermuda, you can run anything you want on this island. You can desalinate the oceans. You can power all your electric vehicles, you can turn off the bunker fuel, and you can live a very pristine and clean environment. And more importantly, we could take care of the other half of our planet, which is energy poor. There's a direct correlation between lack of energy and poverty, and we need to address that as well. So the future that I'm hoping for is one where we have lives of clean energy, where we have a harmonious coexistence of power plants in the major dense cities that are going to use that power. We don't need railroad cars to deliver it. We can put 100 years of fuel on the island of Bermuda in a shipping container. When we get this figured out, we're going to have vertical farming, we're going to have desalination, we're going to have clean maritime transportation, we're going to have electric and hydrogen-powered aviation, and we're going to have a planet where we can maybe match the dinosaurs and get our own 162 million years. Thank you very much.